Hello everyone, welcome to our presentation on communication for unmanned underwater vehicles. In our modern world, we take high-speed wireless data for granted. Our cell phones and Wi-Fi rely on radio frequency, or RF waves, to transmit massive amounts of data through the air seamlessly.
These everyday technologies function perfectly because terrestrial air acts as a low attenuation medium, allowing high-frequency electromagnetic waves to travel long distances with minimal energy loss. However, when we deploy unmanned vehicles into the deep ocean to map the seafloor or conduct research, this convenient wireless framework completely breaks down. But what happens when we submerge that technology into the ocean? Suddenly, our signals vanish. Radio frequency communication becomes completely ineffective underwater. As an underwater vehicle attempts to broadcast an ordinary high-frequency omnidirectional RF signal, the electromagnetic wavefront stalls almost instantly. The moment these electromagnetic fields cross the boundary from a non-conductive medium, like air, into a highly lossy medium like seawater, they suffer catastrophic attenuation. Within mere fractions of a millimeter, the signal is entirely snuffed out, resulting in a total loss of connection.
To understand why, we have to look at the physics of the medium. Seawater is not like air. It is highly conductive because of dissolved salts, represented by conductivity. When an electromagnetic wave hits a conducting medium, it induces electric currents that rapidly dissipate the wave's energy as heat. On a microscopic scale, the incoming time-varying electromagnetic field forces dissolved sodium and chloride ions to rapidly oscillate back and forth, following Ohm's law in a lossy medium. These forced conduction currents convert the organized electromagnetic wave energy into random thermal energy. This heavy attenuation means standard high-frequency RF waves can only travel a few centimeters before dying out. The fundamental physics governing this issue is called skin depth, represented by the Greek letter delta. Skin depth is the distance an EM wave can travel before its amplitude drops to about 37% of its original value. As you can see from the formula, skin depth is inversely proportional to the square root of the frequency. Because seawater behaves as a strong conductor where conductivity is much greater than the product of angular frequency and permittivity, the mathematical relationship dictates an exponential decay. As the signaling frequency increases along the horizontal axis, the maximum penetration depth drops down to zero exponentially, explaining our lack of underwater Wi-Fi. Because seawater has a high conductivity of around 4 Siemens per meter, typical RF frequencies like Wi-Fi or 4G have a skin depth of less than a millimeter. To bypass this, we can drop the frequency dramatically into the extremely low frequency or ELF band, ranging from 3 to 30 Hz. By minimizing the frequency variable in our skin depth equation, we physically expand the boundaries of the skin depth. This enables strategic naval stations to broadcast massive elongated waves that can successfully pierce deep ocean barriers to reach submerged UUV. However, ELF has massive drawbacks. The data rates are incredibly slow, sometimes taking minutes just to transmit a few characters, and the transmitting antennas must be tens of kilometers long. Sound waves are mechanical, not electromagnetic, meaning they bypass electromagnetic skin depth entirely. Acoustic transducers pulse physical pressure waves through the fluid medium over vast kilometers. In the blue and green spectrum, specifically wavelengths between 400 and 550 nanometers, the attenuation coefficient of seawater drops to its lowest point. At this specialized visible light valley, dielectric and molecular absorption losses drop significantly.
To summarize, communicating underwater requires managing deep trade-offs in electromagnetic propagation. Designing effective UUV systems relies entirely on blending these electromagnetic and physical principles together to unlock the mysteries of our oceans. Whether balancing frequency against attenuation, bandwidth against antenna size, or shifting from EM fields to mechanical waves, each option serves a unique operational purpose. Thank you for listening. Our academic references are displayed on the screen. Now,